Today we're looking at continuously compounding interest. This is a variation of the standard um, exponential growth formula. Y is equal to a times 1 plus r to the t power. The problem with this formula is that this describes growth as it occurs once at one period in time. For instance, if you substituted a number in here for like the years, like 10 years, it only calculates the growth one time over that entire 10-year period, which is an issue because most growth doesn't happen just one time. It happens continuously. Most growth is happening all the time. So we have to have a formula that describes growth that's happening all the time, continuous growth. And that's our formula here, A equals P times e to the RT power. This formula describes continuous growth, specifically continuous growth when we're referring to compounded interest, like in a bank account or like a loan or something or an investment. This is what our problems are going to be in reference to. But this formula can describe other types of growth as well. The important thing is that this is describing continuous growth. So if we're describing continuous growth using this formula, A represents the calculated amount, P represents the principal or starting amount, E is the Euler's number, the natural base of exponents, R is the rate of interest as a decimal, and T is the time in years. First example here, if you invest $1,000 in an account that is compounded continuously, this is the key that we're going to be using this formula, P times e to the RT. With an interest rate of 5.5%, how much will be in the account after 20 years? All right, so P is our starting amount, that is 1,000. R, that's the rate, 5.5%. However, we do convert this to a decimal, dividing it by 100. T, time period, is 20 years. So this is going to be pretty easy to calculate. We just plug it into the formula, 1,000 times e to the 0.055 times t power. And this is something we can just put into a calculator. So e raised to the power of 0.055 times 20, which is like 3 point something, multiplied by a, whoops, I divided it by 1,000. Let me try it again. So e 0.055 times 20 power multiplied by 1,000, and we get about $3,004.16. That's how much we have in an account after 20 years. We're going to skip over the second example here, which is pretty much the exact same thing. It says how long to take the account to reach 50. Oh, sorry. At the second example of the PowerPoint, which says start with 500 and how much do we have after 50 years, is pretty much the same problem. So we're going to skip to the third problem. The third problem says a savings account with an initial investment of $5,000 is compounded continuously. So that means we're going to use this formula, continuous growth, at a rate of 2.3%. How long will it take the account to reach $15,000? So we have our starting amount, P, 5,000. We have our rate, which is 2.3%, converted to a decimal is 0.023. And we have our final amount, which is $15,000. Now, you'll notice this is a little bit different because they actually already give us our final amount, 15,000. 15,000 equals 5,000 times e to the 0.023 times t power. As you can see, we're not actually calculating this yet because what we're trying to figure out is the time, and the time is up here in the exponent. So we have to solve this like an exponential equation. there's a few steps to solving an exponential equation. The first is to isolate the base. In this case, it's the base e. Currently on the right side of this equation, base e is being multiplied by this 5,000. So we have to get rid of that to isolate it, dividing by 5,000. So 15,000 divided by 5,000 is 3. So 3 is equal to 0.023 t. The next step is going to be to change this into log form. What changing to log form allows us to do is actually access the variable in the exponent. Change this to log form, so we have a log base e, which is the natural log. Natural log of 3 is equal to 0.023 t. At this point, we can now solve this for the t time period, which is being multiplied by this number, so we can divide by it, 0.023. So that leaves us with t, which can be calculated by taking the natural log of 3 and dividing that by 0.023. This is something that can be done in the calculator. So the natural log of 3 divided by 0.023. That gives us 47.76. So we'll say about 48 years. We'll just round it up to 48 years. So it will take this account 48 years to reach $15,000. Our last example here. A savings account with an initial balance of $20,000 is compounded continuously. After 20 years, the account has $44,510. What is the approximate interest rate? Okay, so once again, we're not just plugging in because we already know the final amount. Final amount is $44,510. The initial amount is $20,000. The rate is unknown to us, and the time period is 20 years. So our formula, 44,510 is equal to the initial amount multiplied by E to the RT, so R times 20, which is 20R. Once again, we have an exponential equation here. Our variable of interest is in the exponent. So we're going to have to handle this by solving this. First, we need to get the E by itself. So we divide 44,510 by 20,000. Gives us 2.2255. That's equal to E to the 20 times R. We can now turn this into log form, which will allow us to get to the variable up here. So the natural log of 2.2255 is equal to 20 times R. And we can now solve this for R by dividing by 20. So we're going to put in the calculator to find the rate. We're going to put this into the calculator. The natural log of 2.2255 and divide that by 20. It gives us about 0.0399 repeating. Well, it's a bunch of nines at the end here. Now, if I were to give an estimate or approximate of what percentage this is for my growth rate or my rate of increase, I would say this is about a 4% increase. You move the decimal over, you multiply by 100, it's like 3.999 or 4% growth. And that's it for topic 10.